automated species identification rather than automated sound. You can ask value about automated sound identification. Examples of some current research, so particularly things like grasshoppers, crickets, bush crickets, insect pests, and something on tree health, and then a little bit about the way forward, or one of the possibilities for forward research, future research, on one of the solutions. So, acoustics. When I go, ah, what happens is you get a sound pressure wave, which has pressure, high, low, high, low, high, low pressure coming along, and it produces a sound, which is, in this case, I can't do a sine wave, but it's an ah type of sound. So here we have electrical signal that goes into a loudspeaker, which causes the pressure, or the position of the loudspeaker to vary, which then causes the sound pressure wave. And at the other end, good over here, sound pressure wave is converted into electrical activity, neural activity, and then that goes into the brain and gets interpreted as the sound ah. Okay? So that's the basic idea. So it's actually a compression wave. And that compression wave can be inside a material, it can be in the air, it can be underwater. Obviously can't be in space, but it can be just about everywhere else. If we're going to measure sound pressure level, we need a measure, a way of doing it, and we generally call this the sound pressure level, or the SPL, and it's measured in decibels. And it's a log of the sound pressure level divided by the reference pressure level, which is usually taken as the threshold of hearing. But, and this is the thing that people don't realise, is that if we increase the sound pressure level by 6 dBs, that's 2 times the pressure. In other words, it's twice as loud. So 6 dB increase is twice as loud. 20 dB increase is 10 times as loud. So when we look at a graph like this, where we have 60 dBs is a conversation, 66 dBs is twice as loud as 60. So 70 is quite a lot bigger, 3 times as loud, 80 again, and again, and again, and again. So all these values actually go up by a factor of 2 every 6 increase. So 60 dBs to 150 dBs is a huge, huge increase in sound level. People don't seem to appreciate it. They go, oh, 6 dBs, oh, it's only 6 dBs bigger. It's actually twice as loud. The red section there is danger level. In other words, if we have 90 dBs for a certain length of time, we can cause hearing problems. If you have 150 dBs, then your ears go bang very quickly, and you end up with perforated ears. So things 150 dBs. But a busy street is about 80 dBs, and the conversation is about 60. If I went quiet in here, it's between 30 and 40 dBs, depending on what the other sounds are. So, that's a little bit about acoustics. What about bioacoustics? Now, there's a very definite distinction between bioacoustics and human acoustics, even though humans are biological things. What I'm going to talk about today is non-human biological origin. Divided into two different types of sounds. One is deliberate sounds for communications, and the other one are incidental sounds, such as feeding sounds, moving, flying. You hear a mosquito. Well, that's usually the male, which isn't going to cause problems because the male doesn't bite you. The female, it's the silent one that comes along and you can't hear it. Bites you. Typical types of bioacoustic signals, so we're looking at airborne and waterborne. So infrasound, elephants can communicate very long distances using infrasound, which is well below 20 hertz, below our hearing. Audio is between 20 hertz and 20 kilohertz. Ultrasonic is 20 kilohertz upwards. Rats, bats, dolphins, bush crickets all produce ultrasound. So these are airborne and waterborne. Then you've got substrate-borne, which is basically sounds going through the whatever substrate it is, wood or whatever. And these can be audio, so feeding sounds of insects, wood boring larvae, plant hoppers. Psyllids are little tiny insects which create the most amazing noises. I don't have any examples today, but if you look up psyllid, acoustics, you'll get straight to a Natural History Museum webpage and just listen to some of the sounds. They're just fantastic. Then you have the ultrasonic substrate borne, which is primarily cavitation implants, which I'll talk about in a little bit. So this gives you a rough idea of the frequency ranges of different animals. The human is in red. Now, my hearing is pretty poor. The older you get, the worse it gets. And it's usually the higher frequency end that gets shot, gets reduced. But things like dolphins, way up into ultrasound, elephants down into infrasound, mice up into ultrasound, bush crickets can be anything from audio upwards up to ultrasound, even cod, fish. Somebody's measured the sound response of a fish, and it's way down in the infrasound up to about 5 kilohertz or something, 500 hertz or so. Chickens, penguins, people have done all sorts of measurements to look at these. And what we're going to do today really is look at the audio things, because I can then play you sounds.
I have a question. So people with poor hearing, so do some frequencies are excluded from their hearing, or it has to do with intensity as well? Like
it's both. It's both. So in my case, if I had a very, very loud 11 kilohertz sound, I could hear it. There's a quiet 11 kilohertz sound, I can't hear it at all. So my hearing goes off at 9.5 kilohertz, which is really irritating, because all the bush crickets that I want to listen to, I took some interns to a nature reserve last year to do some recording work, and these bush crickets sing at about between 10 and 15 kilohertz, and they were all going, "There's one over there." Where? There's one over there. There's one over there. Oh, I can hear another one over there, and that's a different sound. Oh wow! So I had to get a back detector out, and I could pick up with the back detector. So I was a bit annoyed.
I just have a kind of not really scientific question. So these are the ranges what we can actually recognize, but so does it have an effect? For example, if you hear like an infrasound, does it have an effect on us?
It can do. Okay. Infrasound in particular, because it's very low frequency, and in fact there is some work has been done on military type of applications of infrasound, where you can actually burst people's kidneys. And somebody once designed an infrasound amplifier which could destroy houses. So yes, I think about 6 hertz I think is your kidney. Don't quote me on that, please, and I'll have to record on. So yes, you can. Ultrasound can have an effect. In fact, some people reckon they can hear bats, but they're not hearing the ultrasound, they're hearing a demodulation in the bone. So it's very, very loud. I'll play one in a second. It's a very loud sound, and it actually gets demodulated, so you hear this click, 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 and as the bat is coming past, you can hear it. But you're not actually hearing the actual ultrasound. You're hearing a demodulation in the ear. And in fact, here we go. Now I hope this isn't too loud. If it is, I'll turn the volume down, but if it isn't, then it's volume. Right, cicadas. We only have one species in Britain, and it's ultrasonic, so we can't play that one. Okay, now there's many different species of cicada. Some are very, very distinctive, some are very boring. Stag beetle larvae, now this actually makes a sound inside a piece of wood, so inside a piece of wood, and we don't know why, and it's a deliberate noise rather than a feeding sound. And it's rubbing its middle and back legs together, like a grasshopper does. Well, the grasshopper doesn't rub its legs together, but nobody knows why. Now, bats, if we want to listen to bats, what we do is we mix the sound with an ultrasonic signal and bring it down to audio. So what you'll hear here are the echolocation calls. Okay, so that's a very high speed, decreasing frequency. They call them chirps, and that's the echolocation call. I like that one.
Play it again.
Play it again. Play it again.
Could be.
And when they get close to an insect, the speed of the echolocation goes up, and you can end up with a thing called a buzz, feeding buzz, and it goes. And that is exactly what it sounds like. So you can hear with the back detector, he goes, oh, it's just caught an insect. And then this is underwater. This is an insect underwater singing for a female. This is a male. And it's actually singing. And then you have sounds like feeding, insects that are feeding sounds. That's the original Very Hungry Caterpillar.
Yeah.
And then you've got this, which is a beetle larva, which is quite, a moth larva, sorry, it's quite a big one. And what it's doing is it's biting. It's biting the fibres of the wood.
Have you thought about like getting in contact with the music department and doing some collaboration
Oh, yeah.
with these sounds and
Yeah.
adding it to some experimental music?
Oh yeah, we've done that. We've
Yeah.
done that. A couple of years ago, about 3 or 4 years ago, I had a final year student project. It was looking at not these sounds in particular, but looking at environmental sounds.
Yeah.
There'll be more as we go through, if I can fit it in. So, computational bioacoustics is basically even making sounds for music is computational bioacoustics in a way, because you're using computation to do things. Primarily, things like recognition, sound recognition, and it's related to speech recognition and things like computational auditory scene analysis. But remember, I'm not applying it to human sounds, I'm applying it to non-human. So we can look at species identification and sound identification, which is soundscape research, which actually involves species identification. So, why is species identification useful? Well, first of all, manpower to go out and listen to the birds going tweet, 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 and you go, oh yes, there's 15 species there, and I can't afford to come out for another 3 weeks. Spend an hour, another tweet, 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 and you don't know what's happening in the 3 weeks in between. So we can actually start to work on automated ecological surveying by listening 24 hours, 100% of the time, and identifying all the sounds. We can also do it quickly. In other words, within 24 hours, you're expected to get nearly all the species of bird that are singing in a particular site, compared to spending 3 weeks doing it on and off. Education and training, this is a good example. It's not a very good picture, I'm afraid. It's in Japan. I'll show you where in a minute. And that was using a Sony PDA, which is a precursor to a mobile phone, and a microphone, and it was used to train children to recognise birds. And it had a bird recognition system on it, only 20 birds, and it was very, very slow. But it actually worked, and that was about 10 years ago. Long-term continuous studies, things like habitat loss, climate changes, reducing the undersampling problem. In other words, if I listen out here once a week, what happens in the intervening time? You know, I get 10 species today, 10 species next week. Does that mean there's 10 species all the time? Because it doesn't, because you might get 11 tomorrow, 20 the next day, because it's a big migration day, because we have no idea, because nobody's monitoring. So this long-term continuous can do things like that. One thing that has become a real big problem is that there are many, many species and not many people to identify them. So taxonomists are the people who do the species identification. There are no degrees in taxonomy in the UK. There's probably one MSc in taxonomy in the UK, so we're not training anybody. So if we can do automated identification, we can help out the taxonomists, because there aren't enough taxonomists to do all the work. Discovering new behaviour, I'll show you something on that later. And early detection and identification of pest species, which I'll talk about later. But why is it we haven't got this already? Well, there's been a huge resistance. The taxonomists in the old days, as in less than 10 years ago, thought they were going to be replaced by technology. So they were worried about their jobs. Even though we kept telling them, no, these are tools, these are to aid you, they're to help you. Technological advances are helping, so basically everybody who has a smartphone nowadays now realises just what you can actually do with these things. Biggest problem is multidisciplinary funding is really hard to get. So, the electronics department applying to the Biological Research Council, they go, what? Yeah, it's not easy. The problem is incredibly difficult, isn't it, Freddy? Imagine, driverless cars. How long has it been when people have been talking about driverless cars? Speech recognition. In the 1960s, they said by the 1970s we would have typewriters that you could talk to. Never happened. 1970s, they were said by the 1980s, and so on. And now we've got Siri, Cortana, and Hey Google, or OK Google, whatever it is. Now they work, but I think you'll probably find that they don't work very well. And the biggest problem is if you've got somebody with a strong accent, like a Scotsman or Welsh, then it can cause major problems. Either few words for anyone or lots of words for a few people. In other words, the system is usually trained on relatively small numbers. But then that's only one taxonomic group. All right, there's lots of languages and lots of people with lots of variation, but it's only one biological organism called a human. How many bird species are there in the world? How many mammals are there? Amphibia, insects. 10 million species of insects, of which probably 1 million make noises. That is a completely different ballpark from humans, so that's why it's hard. Isn't it, Faddy? Sorry. So, many species, problems with similar sounding species. Two species which sound very similar cause big problems. Problems with lots of things singing at the same time. And then we've got sounds outside the human hearing, which isn't a problem because we can use microphones or vibration to pick that up. So, a couple of examples. Now, this dawn chorus has a bird in it, which has another problem which we may not be able to overcome, which is mimicry. It sounds like a mobile phone. That is not its normal song. It's heard a mobile phone. And there are cases of birds imitating alarms and all sorts of things. The other problem we have is, this is the ecology pal where the Japanese people are doing their sounds, is if you look at the daytime, ducks, vehicles, splashing birds, and in the second, most of those sounds are in the distance. Birds, quiet, and a very loud single bird very close to the microphone. So we have this problem of near-far as well, because if you amplify everything from a distance, the sounds of the nearby get too loud. Now that's the same side to the different side of a slightly different day, complete with the Japanese ambulance driving down here, or down there, plus the aircraft from Narita Airport. So we have problems like that. So that's a quicker way to do it. Then if you go to the night time, it's totally different. So we've got this problem with lots of different, and you can hear there, lots of simultaneous sounds of different species. We've got man-made sounds, we've got multiple simultaneous, and we've got temporal variation. And all of that has to be done in some form of automated identification system. No. Another problem, this is some British cricket. We only have 6 species of British cricket. In fact, the tree cricket is only not really British, it just appeared in the country. Mole cricket, these are different frequencies. These are the ranges of frequencies over which they sing. And the two we're interested in, the house cricket and the wood cricket, sing in the same frequency. Now, I had a postgrad last year, did some testing work using a recognition system. So these are the different species of cricket singing. So this one has recognised that as a field cricket, that as a house cricket, that as a mole cricket, that as a tree cricket, and this one at the bottom, well, it's either a wood cricket or a house cricket. Now notice that the wood cricket and the house cricket have this overlap. So this is just based on frequency, nothing else. And if I play the house cricket, and I play the wood cricket, it's the same frequency, but it's much faster. And that doesn't take any account of the information about the speed at which the syllables are being produced. If we add that in, that becomes 100% accurate. So this is 100%, 100, 100, 100, 100, 100, and interference, misidentifications, and that's a very important thing. We can't really have a misidentification. So let's have a look at some examples. This is work I've been doing here at the university. Used time domain signal coding features and artificial neural network for classification. Using natural sounds, in other words, we're not using laboratory-based recordings, we're actually using real sounds from the field. Althorp Commons, just about 10 miles east of here. Biggest problem we had is we're only interested in the grasshoppers. There's only 4 species singing, potentially singing. Low signal level, they're not loud. You know, you can't, they're not very loud. But the problem we had was we had birds and other insects, wind, rain, cars, tractors, motorbikes, and the biggest problem was aircraft. So in the end, I thought, okay, right, we want 4 grasshoppers. So what we'll do is we'll train the recognition system to recognise the 4 grasshoppers, fly, as it flies past. 2 cars, types of car, different road surfaces. 4 birds, that's alarm calls and a chiff-chaff. An aircraft, and then a background, which is wind. And just to give you an idea, I won't go into the background on time domain signal coding, not here. I can do it later for you if you're interested. But that's the mottled grasshopper, so that sounds like zzz, zzz, zzz. You can see zzz, zzz. I'm not going to do the others because they're complicated. But the A matrix, this is the feature set that we put into the recognition system, and basically all the 4 grasshoppers are really close to each other on the bottom left-hand corner. If we look at the aircraft sounds and the car and the fly, you notice that the grasshoppers were just down in the corner, and these are all completely different. So on the basis, we can actually, first of all, say we can recognise the difference between a grasshopper and all the others. But we can actually recognise the difference between different grasshoppers. Ignoring that, these are the best results. So for the common green grasshopper, it was 100% recognition accuracy. That involved all the other sounds as well, so we're not just recognising the 4, it's out of 13. And the lowest was Jotricus parallelus, which is the meadow grasshopper, which is just over 80% accurate. Which, considering that was trained on 13 sounds, it's actually not bad. What you can then do is take 2 seconds of a continuous sound and say, what is the dominant sound inside this 2 seconds? And this is the 4 species of grasshopper. So here it's common green grasshopper, common green grasshopper. There it's a bird. There and there is an aircraft. There's a bird. And there's a common green grasshopper singing. So it's taken the most important sound. So if I play that, there's the, you can hear the plane taking off, then here, and the plane still in the background, and then the bird. So this is an early stage automated identification of a soundscape, effectively. We can also do it underwater. Now this is the water boatman again. Now what I will do with this is I'll play the water boatman. I'll play the pond snail in a minute. It's amazing sound. So the water boatman's here, and it says, oh, there's a water boatman, there's a water boatman. Oh, interesting, there's a water boatman there, and there's a water boatman there. That is very faint. When I play it, I'll point it out to you. So, here, very faint. Just before the first one. So there's actually, I thought there was only one in the pond, and there's only, there were actually 2. So, I trained it to recognise a pond snail, and there was no pond snail. So, this is what a pond snail sounds like. Now, think about how a snail eats. It's got a radula, it's grapes. Now, actually, there's two snails, a big one and a little one. Because obviously a small one makes a higher pitched sound than a big one. So that's your 2 pond snails in there. So we can do it underwater. Next one is something we did last year, which is a speckled bush cricket. And it produces an ultrasonic call, which is a real pain because it only occurs at 40 kilohertz, which is way outside anybody's hearing, so I have to use that detector. And we needed a system for monitoring this because it's only found in 3 places in Yorkshire. Nobody knows why, it can't fly, don't know how it's got there. That's the female, completely wingless. The male has attenuated wings and it uses the wings for making the sound, so it just goes like this. And it produces a click. The click is, funded by the Natural History Museum. We wanted one or more species of grasshopper or cricket. We actually used just one in the end. To ultrasound, way up in the ultrasound. But this processor actually is capable of doing Fourier transforms in real time, which is brilliant. Now the actual thing looks like this. This is a processor board, and then my intern built the rest of it with a GPS built into it and SD card, and the sensors are separate. So what it would do is it's got a microphone with up to 80 kilohertz, temperature, humidity, light level, 2 sensor heads, data stored in text files so you can just put it straight into Excel and plot the data. Then we've got GPS in there as well. So once the sensor is placed, once the box is placed, there's a sensor head which is up in the tree here. That then works out its own position and then starts logging. And it logs continuously for days on end. And what it does is it detects the bush cricket sound by having a wideband and a narrowband filter, because it sings at exactly 40 kilohertz. If we have a broadband signal, this is to reduce power consumption. So in other words, if there's something in the broadband, it goes, oh yes, okay, let's try the narrow band to try and pick out this exact 40 kilohertz signal. But what it actually produced was quite interesting results. Now, we sum up all the potential calls, and what happens, now I don't know whether you can see this very well, but this is outside my office. So there are no bush crickets outside my office, I know that. That's humidity. This is over 4 days. That's temperature. This is light level. So you can see the light level 4 days. 1, 2, well actually just slightly more. And then we've got this red are the broadband clicks divided by 50, so that's actually way up. And then the green are supposed to be bush crickets. Now if we compare the bush cricket to the narrowband and the broadband, what happens is it gets no bush cricket detections at all. That's the difference between bush crickets and no bush crickets. That's bush crickets, there we go, the green and the red. But the interesting thing is that this red is actually rain and high wind. In fact, we had a major storm that morning and no bush cricket detections at all during the storm, so it actually worked. In other words, the bush crickets ran away. So these are bush cricket detections, or potential bush cricket detections, and what we then do is we apply an algorithm to detect. So these are detections, and you can see where they correlate very, very strongly with the positions. But here, when there's significant numbers of the narrowband, which says, oh, might be bush cricket, there's even more broadband, which says, no, there's no bush cricket, it must be rain. So we can actually then have additional data which doesn't actually exist. In other words, rain, by detecting. That's another one just showing number of detections. But one of the interesting things is that the bush cricket is primarily nocturnal. It does sing in the daytime. And that's a summary of the activity. So there's some 4:45, and this is in November, by the way, so it's actually quite dark, getting dark, and 3 a.m. to 4 a.m. Lots of calls. Now the interesting thing about this is I can actually detect these bush crickets by driving with the back detector hanging out of the window of the car. I know it's probably illegal, a bit like mobile phones, but I can drive around the sites at 30, 20 miles an hour and actually detect where they are because we can hear them about 8 meters away. And they click. Paddy's heard the sounds of you click, like this, and they're very, very distinctive. So that's one application. It's only one species, and all that work going in for just one species. Next one, invasive insects. So here we go. Pass those around. That is what the larva does to the tree, and that's the beetle that does the damage of one of the species. And there's another larva there. That's what they look like. Now, you might be thinking, well, they're economically damaging. Yes, but what? Well, that's the type of value. How somebody actually worked out that it was going to be £450,948. And what happened to the last two? 950.
Mm-hmm.
Somebody just multiplied numbers up. But this particular beetle, the Asian longhorn beetle, in America, it's cost at least $249 million worth of damage in terms of tree loss. By December 2006, more than 400,000 trees have been removed and over 97,000 trees have been treated with a pesticide. If it got established in the UK, that is the potential damage. It's £1.3 billion. That's loss of trees, loss of amenity trees, loss of forestry, because these things leak basically anything that isn't a conifer. They love it. They love acer trees and all sorts of things.
What's their range in the US? Like, are they primarily warm weather?
No, they're from New York State.
Wow.
They'll survive in this country.
Yeah.
There's a larva. That's about as big as my little finger. Good size. And that was in Milan from a Milan infestation. And they're the exit holes that the beetle chews to come out. And this is the sort of damage in a tree. You can see here all the holes where the larvae have been. And that's a 50p piece, that's a UK 50p piece, so you can see the whole damage. And those trees have to be destroyed. In fact, in Canada, you even have these regulated areas where you're not allowed to move firewood because they may have larvae in them. So by law, you can't move things around, and that could happen in this country if we get to the point where these things are established. So, use vibration detection to detect the feeding sounds. Fractal dimension detection, which is a novel method. But there's a sensor, not very big. Classification using artificial neural network. And these are the types of sounds. This is from the lab at Ferry. Because these are quarantine species, I can't have them here. Because then, whoa, you can't have them. They're not even, they have to have a license to have them in this country, never mind anything else. And this is the feeding activity. So every one of those vertical lines is actually a feeding bite over 3 hours, and that's over 5 minutes. You can see very, very active, and it's basically as it's feeding, and you can hear them from a distance. So, we've been looking at bonsai trees, which are very high value trees, and using multi-channel detection systems. So there's a 16-channel detector. There are the sensors attached to the trees. It records for 3 days continuously, and then determine whether any of the trees have got larvae. Because at the moment, what they do is they take 2% of the crop, the imports, and destroy them. When you've got £3,000 bonsai trees, the bonsai importers don't like you destroying the trees, but that's the protocol. You have to randomly destroy trees to see if there's any larvae. Similar thing, this is quite novel. Some poor woman, or man, I don't know, was lying in bed one day, and they just bought a headboard from a very well-known company, and they heard this. Sorry, just trying to get there. Now you imagine that behind your head. And it's a padded headboard, right? So my postgrad and myself visited the thing and destroyed about 1,500 quids of them. Things which is great fun. There you go. All these headboards completely destroyed. It was great. I had a really destructive day. Now, that was the lava was found in the headboard. It would actually cut it up into 2 centimetre pieces, and they found it. Then, a few weeks later, this came on the sun. Now, the strangest thing about this is, strange goings on, strange. They are called Christine and Nigel Strange. So that's their pun on. Okay, our sofa is haunted. Now, they recorded this from their sofa. Now, does that not sound a bit similar? Sort of a little bit similar. Anyway, when the Forestry Commission got hold of it, or Ferro got hold of the sofa, they destroyed it completely into 2 centimetre cubes and couldn't find anything. So maybe it really is haunted. But that was on Have I Got News for You, the programme. And they said, nobody in the world knows what this is. And my postgrad was watching the programme and he said, I know what that sound is. But we never proved it because we could never find it. Then we had another interesting day. That's my postgrad and he said, still. There's a piece of wood with a sensor on it. And they had 30,000 young bare-rooted acer trees being imported into Holland, and they discovered some larvae inside the trees. So they destroyed all 30,000 trees, but kept a few with the larvae. So they rang up and said, would you like to come over and do some acoustic recording of all these larvae in these trees? Yeah! Because we can't get hold of them. Because every time we got there was an interception, they'd ring up and say, can you be in Southampton tomorrow morning? Yes, okay. And we'd ring up 10 minutes later, sorry, we've already destroyed all the trees. So we can't get any. Anyway, so we went over to Wageningen in one day, all the way to Holland and back in the day. And my postgrad sat there, we listened to these things, put the recorders on, and I went off and gave a presentation like this. Came back and he was looking very, very sad. And the person in charge of the group was looking even sadder. So, what's happened? And he said, well, we've got no recordings. Oh, why? They're all dead. And because they'd had to chop them open to see whether they were alive, they put them back in carefully because they'd all dried out and died. So if they'd have checked them the day before, they could have rung us up and said, don't bother coming, because they're all dead. So we had a day in Holland proving that dead insects don't make any noises. It's good fun though. Then the final section is, I mentioned tree health. Well, it's fairly obvious that things that feeding inside trees cause problems, so the tree is not healthy anymore. So we've got things like pest and alien invasive species. That's not aliens from up there. That's the definition. Disease is mechanical stress. Now at the moment, people actually use acoustics. They actually have devices that they put around the tree, listening devices, and a hammer, and they go bang, and it measures the acoustic propagation inside the tree. If there's any damage inside the tree, you can actually detect it. But it takes about half an hour to set up, so you can't do many trees in a day. Vibration detection we've already looked at, and the spectrum of sounds can go from a few hertz right up to 400 kilohertz, which is cavitation sound, which is the sound of bubbles bursting because the trees, if the trees are water stressed, instead of the water going up in, you imagine a blood vessel, instead of the water going up through the vessels, you get little tiny bubbles appearing. It's called embolism. You get bubbles in your bloodstream, it kills you. Well, similar things with trees, it kills a tree. First one, mechanical damage. Can we do something about mechanical damage that is automated? At the moment, you have visual inspection, very, very expensive, especially if you need cherry pickers to go up and have a look in the tree, crown of a tree. 2013, a family was sitting just near the Viking Centre, having a cup of coffee, and a tree fell on them, or part of a tree fell on them. And luckily, it didn't hit them. The branches were this thick, and it'd only been inspected 3 weeks before, and passed fit. Now the tree's gone. That was a very nice, apparently there's a very nice Christmas tree there now. But even worse, in fact it happened in Yorkshire a few weeks ago. A branch of a tree fell off at Kew Botanic Gardens and killed someone. So you've got the problem of, and they have no idea when this is going to happen. It can just happen, nobody knows why. So what we really want is some form of early detection system. Then you've got that. Now that was solid oak, and that would weigh at least 5 times as heavy as it is now, but it's so full of holes caused by Deathwatch beetle that you can see here. In fact, this was detection in a stately home, looking at detecting the Deathwatch beetle. I've got a nice story about that, but I don't have enough time today, so I'll maybe tell you at the end. I'll tell you now. I got this phone call from the person who runs and owns Northern Collier Hall. And if you ever thought about a typical English ales, very, very posh, very, 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 very high class. And I got this phone call, I said, hello, I believe you're interested in beetles. And this is what he sounded like. I could hardly understand what he said. He said, we're having some work done, and we've got lots of Deathwatch beetles. Would you like to come and have a look at them? Yeah, all right. So, but it's just this sort of the sketches that people have on the television about English gentlemen being real. It's exactly right. Was in his case, anyway. That's not going on the web, is it? Just edit that bit out. It was absolutely brilliant. It was on the television earlier this year because they fixed it all. So this is a research proposal that was actually rejected, unfortunately. But the idea, still trying to write another one. Can we detect all of these things using acoustics? Using a network. So wireless networks of tree recognition systems that recognise the internal tree soundscape, whatever that might be. Now, because of the time, that's what it would look like. So each one of those is a network. It could be in parkland for old trees, ancient trees, which are trees of very high value, in the forest or in woodlands, or even in urban areas, stressed trees basically because they've got very poor drainage. So what we need to do is to basically do what Faddy's doing, and what Faddy did for me, is to extract relevant features for sounds, apply pattern recognition, and see if we can then extend it to cavitation sounds. Now here's an example of, this is in a dead tree by the way. It actually doesn't sound very good, so I won't show you. I won't play it, but this is the feeding activity of a beetle larva inside a dead tree. And you can see here that it actually tails off. It stops. So presumably it's not hungry anymore. But nobody's ever been able to measure when things are feeding inside trees because nobody's been able to detect them. That activity reduces. We had a huge storm just over a year ago, and I was accused of listening to hugging trees because I was standing there with headphones on and sensors attached to trees. And yes, I was listening to the trees. So we've got an ash tree, willow tree, very high wind. You can see here, this is just the amplitude over time. This is in minutes. And this is the power spectrum, so it's looking at the power. So you can see here that it's high power gives you basically wind. So, let's see if we can listen to some sounds. This is inside this tree. Now, 5, 4, 3, 2, 1, plunk. That's branches. Bang. That is an insect making a noise just by the sensor. Now you might think, oh, that's the same sound, that's the same sound, that's the same sound, and that's the same sound. And in the middle of all of this, it's not haunted tree. It's actually wind noise in the tree. So we've actually got knocking sounds, clunk, 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 insect sounds, and wind noise. And Fadi very kindly stuck everything through his pattern recognition system and came up with this. 91% recognition accuracy for the insect sounds, 88% for the wind, and 80% for the knocking noises. Now that is based on a sound which is only 5 minutes long. So we don't have a lot of history with this. This is just one set of examples that actually show it works. I'm quite pleased about that because that's going to go into the next research proposal. We can also measure pitch contour, which is how tuneful the sound is. And in here, if you look here, the pitch goes up, particularly when we've got wind noise. And this is just an example zoomed in of that. There's a wind sound, which is actually quite tuneful. And you can see the pitch. Starts back there. Gets stronger. And then starts down. It's good sound now. Haunted trees. Then, in the very high wind, we get this. That's all the branches moving around the tree. Okay? Now, that's an ash tree. These are, by the way, just behind the sports centre here. The willow tree sounds very different. And in fact, if we do the pitch contour of this, it's all over the place. But that is very different from that. So we can actually, in theory, be able to use something like pitch just to determine what species of tree it is, which has never been done before. Oh, looks like we're running late. Okay, there's people waiting. Way forward. This is the basic idea. We have a standard system, then we have lots of expert knowledge, which then allows us to change things. So if you're looking for insect sounds or bird sounds or whatever, we can actually train the system to do things. And finally, that's not bad sound. We've got lots of potential, but most of it is still really, really in its infancy. It's really early stages in a lot of this. Tree health is unheard of. That's new. So you're the first people really, apart from Kew Botanical Gardens, when they try to get funding off them, you're the first people to hear a lot of that. Okay, so we've got people waiting outside.
Yeah, thank you very
So,
much.
thank you.
If anyone's got any quick questions, I guess as we pack up, we can ask.
So just in terms of funding agencies, you said botanical gardens. What other groups are interested in this?
Councils.
Councils.
Yeah.
Because of the
Forestry
public
Commission.
danger.
Yeah. Forest Research, Forestry Commission.
Okay.
And so
And
on.
I guess it has a wider application in areas with higher lumber resources like Scotland and
Yeah, and America.
America. Yeah.